As I mentioned in the previous video, there are more than 150 different proofs for Pythagorean theorem. But I think we should check what the Euclidean actually did, right, for that proof. So the following method is in the Euclid's Elements, like the book he wrote about 300 BC. And when you compare the proofs, like what Euclid did, and the proofs that we saw before, his method looks like much more complicated, right? But one of the reasons for that is when he wrote these elements, he actually used the postulate system, which means he's just building up these axiomatic systems, which is so brilliant. And in modern math, like geometry and everywhere, we actually use his concept. We start from a small number of postulates. So without proving it, we just accept them. And using those, and we actually building up the entire system, by the way. So he tried to use some statements and postulate which accepted previously, right? So he has some kind of tied his hands, right? Not that much luxury of using all the known facts, but he tried to just use those tools which proved, right? Which has been proved before. Okay? So it's a little bit complicated, but I think it's a good exercise to practice for some facts in math, especially geometry, right? So through this proof, actually, we can check several different theorems in geometry at least. So let's look at here. For the proof, he actually start with the right triangle ABC. Okay, good. And then at this moment, the hypotenuse is side AB. So he want to prove that area is sum of this one and this one. Okay. And in this case, to show it, actually he separate this largest square into two parts of rectangles. And the way he just cut is actually using that vertex C, right? And sketch the perpendicular line over there. And that's how you separate into two parts. Then it turns out that that area of that rectangle is same as this one. And area of this rectangle is same as this square, okay? The area of the square. So let's just look at in that way, right? So when you look at this one, you don't need to look at those, right? Just this one is enough, okay? So let's start. Over here, let's just compare the FAB, that triangle, and CAD. Let me change the color. Okay, and we want to show them congruent each other. So in math, one of the famous congruent theorem for triangle is SAS, right? So we want to compare each corresponding size and the included angle between them. Okay, so let's look at here. Let's just follow this. Look at the, the quadrilateral, actually ACGF. When we look at it, it's a square. We know that, which means FA and all the other sides are same, but as we can see before, we need AC, right, to get this one. So these two sides are congruent each other, okay, from that square. Then for the same way, how about ADEB? So for this square, we know AB is congruent to AD. Now, if this ACGF and ADEBs are squares, right? Which means that angle FAC is a right angle. And BAD is also right angle, right? So please fill out those portion, right, by yourself. Okay? I'm already mentioned everything, so please write down by yourself. But those two angles, like FAC and BAD, are right angles, right? So the measurement of FAC, the angle FAC, equals measurement of angle BAD, right? So in this case, don't forget M in front of it. Okay? BAD. Now, let's look at the angle between those two, that angle, like a CAB. Then that angle is just same to itself, right? Of course. So when you add that angle CAB to FAC and to BAD, right? Then it's same, right? Because it's 90, 90, oh, sorry, 90, 90, and that's the same angles, right? They should be the same. But when you add these two angles, like FAC and CAB is all together this angle, right? So that is FAB, right? Then that should same as this angle, right? All together. So it's a CAD. Okay? That's the portion here. Okay? So we can claim that angle FAB, the red ones, is congruent to angle CAD, right? The yellow one. Then what we just showed here is, let me just give you a separate shape. Okay? This is FAB. And another one is like this, CAD, right? And we just show this one is congruent to that, and that side congruent to this side, and we just show that red angle is congruent to this yellow angle, right? That means these two triangles are congruent by SAS, right? Side angle side. So if you haven't take the geometry course, maybe this is kind of sound new to you, but I suppose you already took a geometry course in high school, right? So I think it's famous one, right? But anyway, so by that we can show these two triangles congruent, which means that area and the area of this triangle are same, right? That's the key part here. These gray areas are same. Okay? So remember that. Then in the next step, why these gray areas are same? That's the question. So to look at it, please look at this side AF and G with here, right? So the triangle we covered looks like this way, and the square looks like this way, right? Then actually it's a not exactly same, but right, but what's the relation between these two? That's gonna be a question, right? So let me explain this way. When you have a right triangle, let me just do that, and let's say A and B, then the area of that triangle is A times B over 2, right? Then it's just true for the entire square is just A times B, right? So that triangle is half of that rectangle, right? That's clear. Now then, when you have same base and for the same heights, let's say it's B, there's a parallel line to this side. And the first triangle is that, and the next one is like this. Then how about the area of this right triangle and that like obtuse triangle? Actually, they are exact same area. because in that obtuse case, still the area formula is what? Base times height, right? And divide by 2, no matter how it's tilted, okay? So when you compare the area of this triangle and the area of that rectangle, when you look at just half of it, then this triangle area is exactly same as half of this square, right? So it's a double of that, okay? And the previous step, we show this area is the triangle is same as this one, so that is also 1, right? But when you look at these two, we are already having same area 1 like that, but this one is also double of this one, right? Because when you look at this square, when you just look at that triangle, then that is same as this gray area, and that is half of this square, right? It's a rectangle, of course, in this case. So the area of this rectangle should be 2. Now it means what? These two areas must be same, right? So please rewrite the reasons for that, right? For each, okay? And this one. So what is the conclusion of that? In that given ones, have to have this, that area of rectangle is same as the area of this square, right? Then when you look at the other case, when you flip it, actually this one should be same as that one, okay? Just the same way. So in the next step, you have to do this one. So area of BCHI is equal to the area of the quadrilateral BJKE, right? For this one. So altogether, the sum of ACGF and BCHI each is same as area of this rectangle and area of that rectangle, which is entirely the area of the sphere ADEB, right? So that's going to be entire proof, which takes much longer and requires more kind of facts, right? A lot. But in his elements book, he already proved and show all these kind of facts, right? So just using those facts is kind of easy proof for that. Okay? But at least, right, we should kind of remember, at least for those kind of proofs we have covered in here, okay? Including the proofs in the homework.